Okay? Now the theory symbols gave us relations among these, right? This is massively over-generated, right? What's the dimension of the S2? It's 2, right? So we really need to pare this down to something more manageable. So the whole point of Manin symbols is that it gives you a way to do that auto-magically. Okay, so I have to tell you 2 slides worth of that. So these are called Manin symbols. In case that wasn't clear. In other words, we're labeling, we replace the paths in the upper half plane with new labels, and they're called the elements of P1 of Z mod n Z. Okay, so we're going to now let SL2Z act on Manin symbols. On the right. And here's what it does. So it's going to take one of these guys and produce another guy. Okay, so the I and the J belong to this set. And what is the definition of this? Well, I define this action via the permutation action. Okay, so somebody came along to you and said, hey, you, I want to have my gamma, which I produced for you, it's an element of SL2Z, act on this symbol I. Okay, so I write down the ith coset. Remember I took those as left cosets. And then I hit it with my gamma. Okay, now I have a new coset. And I call that coset J, and then I map it back here. Okay, so the right action is via the permutation action on the cosets. Clear? Okay, so via permutation action on cosets. Okay, so because it's on the right now, we need to think a little bit more critically about, we need a new matrix which is called R. This is an element of order 3, check the characteristic polynomial, so it's my replacement for ST. And I need my usual S. Okay, so let's just investigate what happens. I don't want to start a calculation here on the bottom. What happens when we start hitting our Manin symbols with these elements of finite order? Well, because they have finite order, we're going to see that it implies relations among the Manin symbols. So this is just a practice to show you, if you were making up this theory yourself, and you were led to this, well, let's relabel our symbols by cosets, I think you would have rediscovered this kind of action too, where now I need to write down not this big generating set, but I need a basis. Okay, so how am I going to pare down my generators to find a basis? Well, I want to use relations somehow, and the natural place to be looking for relations are among elements like this. So r cubed is equal to 1, and of course s squared is still equal to 1, thought of as elements of PSL2Z. So let's practice with this. What if I take one of my guys, I is an element, well, it's a Manin symbol, so you think about that I is in P1 of Z1 and Z right now. And let's compute this I plus IS. Okay, this is like linearizing the action. If you want to think about s squared minus 1, that tells you s minus 1 times s plus 1 is equal to 0. And I'm kind of picking out, dare you write this as I times 1 plus s? Okay, I don't know if you can, if you're prepared to accept that. It's sort of an unfair way to mix notations, but that's what I'm thinking about. So s squared minus 1 is equal to 1, and I picked out one of my favorite factors. Okay, stop talking, John, and compute. You're delaying. Well, okay, this is to say, what's the definition of the brackets I? If you're still with me, you'll recall that this is the definition, where I've chosen that ith coset. My indexing set is the P1 of FP. And here, well, I guess I'm going to have to take my gamma I S. Think for a second about why that's the right thing. All right. So now I can certainly apply my gamma I infinity here and my gamma I 0. What's going to happen with these guys? What does S do? It's going to interchange, right? S is the Z goes to minus 1 over Z, interchanging 0 and infinity, and then I apply my gamma I. Okay, so that looks to me like gamma I 0, gamma I infinity. So what do you get? You get 0. Okay? So what should we similarly take for the r cubed minus 1 equals 0? Well, r is not equal to 1, so the other cofactor would be 1 plus r squared. And I encourage you to similarly check that 1 plus r squared, okay, I don't want to write that, I plus ir plus ir squared is equal to 0. This is for all I. Okay, so we just produced relations among our Manin symbols. You guys got that? Okay, guess what the miracle theorem is? These generate all relations. Just these guys. Amazing, right? The only relations. Theorem. This is Manin's theorem. Hence the Manin symbols. If I take the direct sum over z, or I guess I'm taking q. Version. So I take the q vector space spanned by the symbols I. Okay, how many of those there are there? It's as many as p1 of z minus. Okay, p plus 1 when you take prime. I mod out by the relations that I just wrote down. So I declare that I plus is is 0, I plus I r plus I r squared is equal to 0, and I do this for all I in my P1. Whew, right? Is that it? There's a lot of symbols, but is it clear what just happened there? I took my generating set, consider them abstractly as some vector space, and then I mod it out by, so this is now a finite dimensional vector space, right? Just find a minute. And I mod out by a bunch of relations. So the miracle is this is isomorphic to M2. Yeah. Gamma here is the gamma 0. Where did the gamma enter in here? And it's acting by the cosines. That's how you know that the gamma on the right-hand side was encoded in the left. It's a bit involved to prove, but it's clear if you're sufficiently versed in group cohomology. Everything that I showed you today was just a couple of lines and a nice Shapiro's lemma. You guys like a good group cohomology? Don't be terrified when people tell you stuff like that. It's just motivation to learn, first of all, the concrete version that really gets you familiar with the objects, and then say, well, can I step back and not be so mired in the details? What's the right level of generality to be working in so I can see clearly what's true? And the answer is, this is a nice, fat way of saying Shapiro's lemma. All right, so now I want to do an example, and I actually have some time left, which means I will take a quick question about anything. You guys feeling good about this? So I took an infinite quotient by infinite quotient. Now I'm going to show you how concretely, because now we can just use the, okay, maybe I should stress this, because really this is the point. The reduction algorithm was the whole game here. Do you guys remember 10 minutes ago when I make a Hecke operator, I'm now going to write it down as a bunch of symbols. Okay? What do I do with those symbols? Well, I just use the Euclidean algorithm to write it as a sum of gamma I infinity comma 0, right? Remember our original reduction algorithm, which was the Euclidean algorithm? It takes as input any symbols, and it writes it as a linear combination of gamma infinity comma 0. Do you remember that on the second day? Okay, so now guess what I did was I wrote down a bunch of symbols that are of the form gamma I infinity comma 0. Okay, so I just used the Euclidean algorithm, and it's writing it in terms of the canonical generating set. Okay? And then once I have that in terms of this, well, if I could compute these relations, then ba-bam. Okay? That's the whole point. So that you don't use the reduction algorithm on the fundamental domain. So for gamma 0 of n, the fairy symbol might be complicated and contain all sorts of gorgeous combinatorial awesomeness. And you're like, no way, dude. just tell me about the cosets of gamma 0 of n, because I can organize everything in terms of the permutation character and then use my reduction algorithm from SL2. Yeah? Okay. So let's try with gamma 0 of 11. Maybe this will work. You know, I knew, oh, I forgot. I only got 10 minutes left. Because the lecture's only 50 minutes, I have to shave off 10 minutes from each one of my lectures. But you guys want, I'm going to just show these. Okay, so now for the next 8 minutes, I'm going to show you some slightly horrible computations. And what you should take away from them is, I could do this. I don't need to write anything down. Okay, maybe scribble a few things down, so that, and then forget that I showed you how to do it, and you go and check yourself. Okay? So we're going to have some 12-dimensional vector space that I need to pare down to a 2-dimensional vector space, and I want to compute a Hecke operator for you. You earned it. You came all the way here. Let's compute a Hecke operator. Okay? So here we go. Should I zoom in a bit? Ah, it's coming at you. So what do we have to do to compute with gamma 2? Because I guess I need to compute this action. So what did I start with? I had 12 symbols. They were labeled 0 up to 10 and infinity. Okay? So I need to first take my guys and hit it with an S and see what relations those imply, and then do the same thing for the R. Is that a hard thing to do? Do you have to call up a Sage script in order to? No, you've got a bunch of 2x2 matrices with most of the entries 0, and you're going to apply them to infinity and 0 and some, and then this guy. Okay, so this is something I'm going to show you what it looks like. So I say, well, how does S act on I? The claim is that it acts by -1 over I. Let's think about that for a second. That's not, okay, yep, that's true. And you have to interpret this as the I is 0 means that -1 over 0 is infinity, right? I have the full P1 of things. Okay, so that tells me that because I've declared I plus IS to be equal to 0 according to the relations that I found there in the Neen's theorem, that gives me how many relations? Well, I guess I get to pair them all up. And so I see 0 plus infinity is 0, 1 plus 10, 2 plus 5, so all of the computation is in relating an element A to -1 over A mod 11. Okay, that's the content of the thing I just wrote down for you. Is that clear? Okay, that was too easy. What about the R? Okay, well I claim that similarly the action is given by I goes to -1 over I plus 1. Okay, that's pretty clear then that if I did it R and then R again, that I get back to the identity, which is what I'm supposed to get because R cubed is equal to 1. Okay, so then you're going to get how many more relations? Well, you have to group them up by 3s, and you get something like this. All right, oh crap. All right, so what are we about to do? Well, we're taking like a 12-dimensional vector space, and I'm making for you a subspace. That subspace better have dimension 10, because the quotient is supposed to have dimension 2, right? Well, 3, I guess, because I'm taking the M2 here, not the S2. Okay, so I guess it should have dimension 9. And, well, when you work all of the data out, you find, is that still on the screen? You find a basis of symbols called 0, 2, and 3. Does that look vaguely familiar from what we did with the fairy symbols in terms of the cusps? The answer is kind of yeah. There was an infinity 0, there was a 0, 1/2, and a 0, 1/3. So the 2 and the 3 are, well, okay, we could read whatever we wanted to read into that, but it's, what did I say there? It's just like you would have gotten in fairy symbols, but now we have explicit identifications for all of the other cosets. So that allows me to take something in a 12-dimensional vector space, and you know, even if I hit it to compute the Hecke operators, I can move it back. Right. I think I said that enough times. Here is the explicit identifications, the thing that I jammed in on the right-hand side. Can you read that? I hope you can't, because like I said, this is just a way of rewriting the relations that we wrote down. So all of the other 9 symbols out of the 12, I'm claiming that I can rewrite them in terms of the other symbols. For example, infinity is -0. Okay, so in my basis, is that clear? So it's like I diagonalize my matrix and now I have my pivots. So if I take a thing in the quotient, I know what the kernel is. Okay. Now what? Hecke operator, right? Hecke operator. So how does the Hecke operator work? Well, we have to take our basis of elements. I guess we might as well compute the Hecke operator on all of M2 gamma. No one can stop us from doing that. We'll have to tease apart the Eisenstein piece from the cuspidal piece, but we might as well compute a whole space of modular forms. That's dimension 3 instead of dimension 2. So what does that mean? Well, I have to take one of my guys. So remember the basis was 0, 2, and 3? Okay, so I'm going to practice with one of my symbols. So I'm practicing on T, so I'm taking the Hecke operator T2. What am I going to produce for you for T2? Well, it should be a 3 by 3 matrix. Right? That 3 by 3 matrix means I have to take each of the 3 elements here, do my T2, and then rewrite it in terms of my basis of symbol 0, 2. Okay? So I have a bit of work to do. I'm showing you one of these pieces, which is T2 times 2. Okay? So the definition of square brackets 2 is that it's the symbol 1/2 0. Guys remember that? Okay? What's the definition of the Hecke operator? The definition of the Hecke operator, the theta, the fatty theta. 3 things that I apply to the 1/2 0. Okay, great. So now I have to sum them all up. Okay, that means I have to apply some matrix to get my 3 symbols. Now what? Now I use my reduction algorithm. For the first few, I got kind of lucky. So when I hit 2, 0, 0, 1 with the 1/2 0, I got the symbol 1, 0. I didn't have to do any reduction on that. That's just called 1. Similarly with the 1/4, that's just called 4. Okay, what about the other guy? 3/4, comma, 1/2. Well, do you remember when we did it on Tuesday? I said the first thing we're going to do is we're going to rewrite alpha beta as alpha 0, comma, alpha 0 minus beta 0. And then I'm going to show you how to do it with a single alpha. Alpha is now a rational number, so I use the finite continued fraction to give me a sequence of fractions which satisfy the Theory condition and therefore are given by a matrix in SL2Z once I fix the signs properly. Okay? So in this situation, I have 3/4, 1/2. So first I write it as 3/4, 0, 1/2 0. And I claim that if you carry out the calculation, I'll show you the fraction in a second, but I just want to get to the end of the calculation, that then you end up with something called 7 plus 10 minus 2. Okay? Now you use the relations that are jammed up there in the upper right to rewrite this in terms of the basis. And when all of the dust settles, you shouldn't believe me. You should do this computation yourself. I had to do it a couple of times until I got the answer, which I know is correct. The answer is minus 2. Okay, so in the basis, 0, 2, 3, this T2 is going to be represented by a matrix. And so the 2 would be, let's say, the middle column. And what would I write down as the middle column? The middle column would be 0, 2, 0. Is that clear? Okay, so I promised you a fraction. I promised everyone things. So this is just the proof that I'm not lying to you. So you have to take the, oh, you can't see it. Now you can. 3/4, have you guys done ever one of these finite continued fractions before? I'm just showing, I'm previewing this, and I really, if you like this, I encourage you to do it too. 3/4, you take the floor, which is a 0, you subtract the 0, then you write it as 1 over something. Okay, so 3/4 is 1 over 4/3. Take the floor of that, so you peel out a 1, and then you have 1 over 1/3, and you stop. Okay, because now you have a plus 1 over an integer. Okay, you keep doing that until the next fraction after you do the floor is a 0. Okay, then the algorithm says you write down the convergents. Convergents are when you stop the continued fraction at some point, and you just write down what you have so far. So those would be the 0 plus 1 over 1, and the whole thing. So that gives me 0 over 1, 1 over 1, and 3 over 4. Check that those satisfy the conditions. If I put them in the columns of a matrix, the SL2Z condition. 0, 1, 1, 1, determinant 1, 1, 1, 3, 4, determinant 1. Okay? And then then you just write down the rest of the formula. Okay, so then those fractions appear there, and then, okay, I even wrote these in terms of the coset identifications. Whenever I have a matrix, you see this 3 minus 1, 4 minus 1. The whole point is you want to write that as a coset representative. And I told you how to write that matrix in terms of coset representatives. It's called, you take the bottom row, And you think of that as an element of P1. Okay, so that's your little preview. Am I making sense? You guys happy? So when you finish the computation, well, I'm going to restrict this to the S2. You guys remember that the S2 you can compute is the kernel of the boundary map. The 0 guy is the infinity 0. The 0 and infinity are not identified under x0 of 11. So that's the thing that's not in the, that's Eisenstein. So if you want to restrict to the S2, you can check that this is the basis. All right, you know how the Hecke operators are acting on Eisenstein. But anyway, the thing you get is this. Okay, so what is the point here? Well, do you remember that the dimension of the space of modular symbols is 2G, and the dimension of where G is the genus? So we really do have we'll always get double what we should, like a vector space with twice dimension. There is a natural action of a plus space and minus space for complex conjugation, which allows you to pare it down a little bit more, but I don't want to get into that. So what's the point here is there's sort of two copies of your modular form, with a thing in its anti-holomorphic version, multiplied by I. The whole point is that, well, there was a one-dimensional space of, we'll call it F, and the A2 of F, the conclusion you're supposed to read from this is that A2 of F is minus 2. That's the coefficient of the unique cusp form of weight 2 and level 11. And then I said yes, so I must have gotten really excited in doing this. You remember my F that I made just out of thin air yesterday? And I said, trust me, this is a modular form because eta products. Okay, you don't have to believe me. It is. The A2 is minus 2, and then if you expand this product out, at least it agrees with the A2. I can check the A1, that's also 1. It's the identity operator and all good. So how hard would it be for you to compute an A3 or a T3? I did most of the work already by writing down the bases of elements 2 and 3. You have to do a couple of continued fractions. You have to get used to the identifications of looking at the lower entry. But there's 4 matrices you have to add up. And other than that, it'll be a nice little matrix, 2 by 2 matrix, the diagonal with the right entry. Okay, so that was the big finish. You guys feel like you have seen enough of modular curves, their homology, the representation abstractly as symbols, to give you a concrete way of working with modular forms? I hope so. I did my best to make that clear, accessible, fun. My time's up, so request the organizers the next time they make one of these that the lectures are 60 minutes instead of 50. In the remaining 40 minutes that I was sliced from the top of my lectures, I would have explained to you higher weight, and I would have explained to you what happens if you don't want to work in SL2Z, but you want to work with some other Fuchsian group, a discrete subgroup of PSL2R, at least if it's arithmetic. So then you have a notion of a quaternion algebra whose unit group is acting on the upper half plane. There are replacements for all of these. They're not so simple and combinatorial in terms of cosets, but they have many of the same features. So if you ever want to consider those generalizations, they have all the same flavors: fundamental domain, reduction algorithm, group cohomology, Hecke operators that allow you to compute things as exotic as Hilbert modular forms. On that note, I want to be on record on camera by saying thanks to the organizers. It takes a huge amount of time and energy and part of your soul. Thanks, Liang, and Alvaro and Keith, who are not in the room currently. You guys did a great job organizing it. I hope we'll have a chance, when everyone's in the room, to clap fully for you. But that's the end of my lectures this week. Hope you enjoyed them. Thanks.